Welcome to this week's Happy Maths Hour. Today's called Mirror Mirror, and is it the mirror mirror on the wall? What would happen if you have two mirrors on the wall facing each other? So we might
Caroline,
have what do I do?
We're doing more than mirror mirror. We're doing some tessellation, which is all sorts of
Tessellation and mirror mirror. So we've got Snow White, maybe or maybe not, and lots of other real magic. We've got real life magic rather than fantasy. So I'm Caroline Ainslie from Bubbly Maths. We have Toni Beardon from AIMSEC, and we are both co-founders of the G10, the Global Teacher Empowerment Network. So we hope you'll enjoy and benefit from this show. And it's all about transformations.
Indeed, yes. And so here we go.
Hold on, let me just share it. There we go. You'll know when it's set. Ready.
This is us, Caroline and Toni. Caroline and Toni, and Caroline's the Bubbly Maths person and I'm the AIMSEC person, and we work together a lot. And Global Teacher Empowerment Network, that's teacher empowerment is what we're trying to do, helping teachers for the benefit of the children they teach.
So, and that includes the teachers, include the parents, the carers, anybody who is on a mission to help the children's education.
And in this Happy Maths Hour, we're going to talk about tessellation. Now, this man, amazing, Escher, Maurice Cornelius Escher, he was alive for quite a long time during my lifetime, died in 1972, and I just love his artwork. He made mathematically inspired artworks, woodcuts, lithographs, and mezzotints. And probably because I like mathematics, I just love his art. Now, his work explored space in different dimensions, but in particular, the filling of space by regularly repeating patterns, and they're called tessellations. And he was greatly influenced as a young man by the Islamic art that he saw in Spain. Now, here's some pictures. On the bottom right, you see examples of Escher's art. Can you see the reptiles on the bottom right corner? They're crawling out of the page and over the books and back into the page again.
Yeah, it's kind of hard to see it. You have to look really close to see it. But that's exactly what's happening. They're going from 2 dimensions into 3, and they're tessellated on the 2 dimensions, and then they're actually coming alive and then going back into the picture again.
It's amazing. I just love that. And that above there, you see Alhambra. Now that's
a good point, Toni. So you're leaving. You're not doing the full screen because we can see all of your beautiful.
Oh, okay. I was trying to see. No, we'll have to get a bit. There you go.
That's better.
Much better, yes. Well, I can't see us, but just never mind. It's only because I haven't got a second monitor. Okay, so what you see is some beautiful artwork. That's what I meant when I talked about Islamic art. And you can see out the windows, you can see the Granada in Spain, but on the inside of that wall, lots and lots of artwork, repeating patterns. And at the top, there are 2 photographs of some of those, not the ones on the wall you see there, but other places in that palace, Alhambra Palace. Now, this is what Escher saw, and he was blown away by it. And he wanted to do his own tessellations, and you see some examples of them there at the bottom. And what we have in this Islamic art is evidence of a very sophisticated culture of the Moors. They were in Spain for several hundred years. They ruled Spain. They built palaces like Alhambra and mosques. Some of those mosques are now Catholic cathedrals. And they didn't decorate them with the human form, only with abstract art. And what we see there shows really quite an advanced knowledge in the 14th century of mathematics, not advanced for their time. Now, this is balls for Spain again. What do you like these balls, Caroline?
I think they are charming. I really like, they're grumpy as anything, but they're cute. In their grumpiness, I think they're amazing. I think it's a brilliant tessellation.
I think this was actually drawn freehand because
I'm sure it was.
if you look at them, they are, each one is slightly different, but they're very, very much, very similar. And I think, let's just imagine that they're all identical and they can fit together, and there are 7 of them. They fit together in what we call a tessellation. And can you imagine putting in more bull's heads, spreading this tessellation out over the whole screen and well beyond? Could you imagine this pattern going on to cover a large wall and going on beyond that? In maths, you can go to infinity and you can imagine these balls going on and on, out into the distance. What do you notice about the orange lines there?
Well, they look like rhombuses. They're parallelograms. They each was it the word similar vertex? Each vertex that maps the same one is touching the balls in the same place.
Yes, and what you see is if you just took what was inside one of those parallelograms and then kept repeating that parallelogram, although there's sort of bits of the ball, not the whole ball in the parallelogram, once you start repeating the parallelogram, you can cover the same space and you'll get the same picture with the parallelograms. You'll get the same picture.
Right. So that you get the same amount of space covered by the parallelograms as by the balls.
Yes, but the balls are there inside the parallelograms. It's just that there's only bits of ball in each, well, all the balls there, but he's been cut up and rearranged.
And it doesn't have to be, it's like it doesn't have to be the balls. It can be, it just goes to show you can make lots of different shapes. As long as they map with the parallelogram, it's going to work.
Yes, and you get the same sort of tessellation if you put flowers in there instead of the ball, or trees, or whatever you like, really. And when we talk about the mathematics of it, we talk about how the pattern repeats itself, not what you see in the pattern, whether it's balls or flowers or fish or whatever, reptiles or whatever it is.
Yeah.
So now imagine taking this H shape and doing the same sort of thing with that, drawing a tessellation made with the H shape where they all fit together, and you'll get that.
And I can see the rhombuses. Did you use a different shape?
In your mind, did you join the dots?
I joined the dots. I just went straight to the rhombus that you'd had earlier, and I just made some more. In my mind, I joined the dots on the H's.
So now we see not balls, but H's.
And it's a completely different shape. And yet, it's a similar pattern, what would you call that?
It's a similar tessellation, but is it? Because you could take half the H like that, and you could keep repeating that and fill the same space, or you could take a quarter of the H.
But if you had a stamp that was H shape, all you'd have to do is stamp, 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 stamp. Whereas if you had a stamp that was half an H shape, you'd have to turn it round to stamp the opposite part of the H, or mirror it somehow.
Well, exactly, and that's what Escher did, you see, because when he made his woodcuts, he would have made one ball or one reptile, and then he would have put them into the paint or ink, and then he would have carefully stamped or printed the impression on the paper, and then done it again, fitting exactly as he wanted them to fit into the tessellation. So it was stamp, as you just said, Caroline, exactly. Rather carefully done, but nevertheless exactly as you describe it.
Which was the technology at the time. Yeah, and Escher did all of this without a computer.
Well, exactly. And I think most satisfying, it was real art, wasn't it?
Oh, well, I have seen some of it in person. Oh, my goodness. And if you want to see it, well, the best place to see Escher is in Amsterdam.
Absolutely. And when did you ever go to the Escher Museum there, Caroline?
I haven't been to any museums in Amsterdam yet, but next time I go, I certainly will be going to the Escher Museum in Amsterdam.
Well, what you see there is some of the examples of his woodcuts themselves, not just the end result, but the actual pieces of wood that he used to make the prints. And
in the museum. Oh, really? So you actually see the equipment that he used to make the prints.
Exactly. And I think just sort of thinking about how somebody would make this. In fact, you could do it at home. You could cut something out of a potato, okay, and use that and some ink or paint and
I remember doing that in school. I loved cutting out potatoes and stuffing with them.
Okay, so that's a cheap and cheerful way of making these same sort of prints. And you could make the pattern using a quarter H like that, and you would have to rotate it, and then you could put it into four different positions to make the whole H.
But you can't just keep rotating it, because the one on the bottom, if you've got the top right, the one on the bottom left, oh, that is a rotation, but the one on the top left and the one on the bottom right is a mirror. You actually have to mirror it. You can't just rotate it and stamp it.
No, what have we found in this H pattern? We have found rotations, reflections, and translations.
And translations, which are all the transformations.
And in fact, they didn't exist in the bull. The bull wasn't symmetrical enough, okay? So indeed, although this pattern looks the same, it isn't the same as the bull pattern in the mathematical sense. Of course, it's not the same in that an H is not a bull, but it's not the same in that it's got more, what we say in mathematics, more symmetries.
And there are only so many types of, what do you call it, structures? What would you call that?
Well, they're called symmetry groups. The tessellations that make the wallpaper patterns are called symmetry groups, and there are only 17.
There's only 17 ways you can cover a wall with repeating patterns. So there's only 17. It doesn't matter what the design is. There are just 17 structures, 17 groups of structures.
Yes, the mathematically different groups of transformations. That's what they are.
I'm going to write that down. Mathematically different group. Woo, that's a mind bender. Mathematically different groups of transformations. Right.
Well, let's look at the bull and the H tessellations. You can see that they both repeat the pattern by a translation in the direction of the arrow, and every single point in the picture gets translated by the same distance in the same direction.
Yeah, that's right. Yeah, it's like all you have to do is follow that arrow, and just you move that arrow and you get the next shape. Move that arrow 4 times and you get the next shape.
Well, yes, every point in the picture is moved in the same way.
It's every point. If you move every point, use that arrow to reposition every point in that H. You'll get another H in the right place. Yeah.
Now the H tessellation is based on reflection of a half H. So you get half an H and you reflect it in the dotted line, followed by parallel translations.
Yeah.
Or the H translation can be based on rotations and reflections of a quarter H, followed by parallel translation.
So you'd be rotating and then you'd be reflecting to get that shape down there.
So if you take the smallest piece of the pattern picture and that's repeated, it would actually be the quarter H.
Right. Okay. Okay.
So
you can do this with a quarter H. Okay.
So we've seen something similar about the ball pattern and the H pattern, but actually they're quite different in terms of them, the groups behind them, the groups of transformations.
The H has this one I found very intriguing. The H has a lot more symmetry than the ball.
And yes, so now how could we think about the H, as it were, cut up and fitting into this parallelogram shape? Well, Caroline and I cut this out this afternoon and we tried to do it and we both struggled with it. I found it really difficult.
Toni succeeded before I did. Toni beat me.
I believed it must happen, but for a while I was wondering if it was at all possible, but it is possible, and there's your solution.
And the reason why I'm going to show off with my camera now. The reason why I failed, not the only reason, I wasn't thinking logically about which edges would actually work if they sat together. But another reason why is because I wasn't cutting it accurately enough. It has to be, I cut up another different one and I ended up literally, I thought, I'll be adventurous. I'll cut this one up in different ways. Well, one of the things I discovered straight away is unless you actually go into the edge and actually cut right through the edge, it's not going to work. The lines, wherever you cut there, it's along there, those lines have to be parallel to each other or it's not going to work. That one doesn't matter so much because that angle matches that angle, so that works wherever you end up. But it really matters. The two things that are critical is that you must cut that edge at the edge. You must cut that one right at the edge. Those were the two really critical things. And that line and that line must be parallel or it is not going to work.
Well, the key thing is that you want just as we saw that only bits of the ball, or bits of more than one ball, were in the parallelogram, we're going to put bits of more than one H into this parallelogram.
Yeah, and it really illustrates it beautifully because you take those bits out and put them back on the H, and you've got that's the bit in. Oh, that's not.
And really, it does help your visualization skills to do puzzles like this. I mean, the way I solved it, although I struggled, I have to say at first, was to look at the right angles. And I saw, well, that we had to have a piece that had two right angles and that would fit in the hole at the top, and another piece with two right angles that would fit in the hole at the bottom. One. Yeah. And those are the two, and they sort of, the one at the top had to come underneath and the one at the bottom had to go on the top. And then I was left with these two triangles. And then I thought, I've got to put the right angles together. And again, swapping them over, I found that worked. And you can see it in the solution there. So it's, yes, you have to look at the clues in the geometry, look at the right angles. Look at that. I'm not very good at these puzzles, actually. In three-dimensional puzzles, I know that I've solved the puzzle 20 times before, and I still find it difficult the 21st time. Anyway, let's go on. So what question we're answering is, which transformations of a shape are used to make wallpaper patterns? And wallpaper patterns are patterns that cover a flat surface in a tessellation that can extend to infinity, sort of mathematically in your imagination. It can go on forever. And it could be dress fabric, or it could be curtain fabric, or it could be tiling on a wall.
Or upholstery on a chair.
Yes, and you want to be able to seam or join pieces together, strips together, so that your pattern will extend, or however big your surface, your wall, it will go on, and you can keep, repeating the same pattern. So look at patterns now around you and see how the pattern is repeating itself.
And that's a lovely thing to say, Toni. Be aware of patterns in your life. When you're wandering around the street, when you're noticing buildings, when you're in a shop, noticing patterns, and notice what transformations are involved. And you could wonder, I wonder which of the 17 wallpapers this is.
Absolutely. Now, let's think about rotations and how we use rotations.
Can I just very quickly say, we've got some people watching. If you comment, I can see your comments. So if you do have something to say, please do, because I will respond. We will respond. Thank you.
So what we saw with the H shape is that we had quarter turns. And with those two blue flags, you've got quarter turns to make one flag the image of the other. And the center of the rotation is where you've got the big red spot. So what happens when the flag A1 is rotated anti-clockwise by a quarter turn of 90 degrees, if you want to give the degrees, the flag A1 has the image A2. But you could rotate the other way, and A2 would then go back to A1. So that would be a clockwise rotation. Now, these two black and white pictures here were on a mural, on a wall, painted on a wall, on a house in Africa. And in the picture I clipped them out of, there was a lady standing there in front of it, and behind her this lovely house with these murals and a lot more decoration of this type. But I think they show very much different, very well different rotations. Now, the one with the sort of squirrels on it, the middle one there, that shows what happens if you do a half turn. If you do a quarter turn, it doesn't match itself. What you want to do is with these patterns, you want to do the transformation so that when you see the result, it looks exactly as you see it now. So if you were to rotate that middle pattern there by 180 degrees, a half turn, we call that, it would look exactly as you see it now.
I'm showing it with an eraser, Toni. So I've got a rectangle, and if I rotate it 90 degrees, it isn't exactly the same. Whereas if I rotate it all the way around, it looks exactly the same.
That's a good way to show it. But here we've got a square, and you see that shows rotational symmetry, and we say it's order 4 because you sorry, that's wrong. It's order 2.
2.
Yes.
There's only 2 positions where it looks exactly the same.
That's half turn. Now, what about the one at the bottom there? Describe what happens when this pattern is rotated.
It has 4 positions where it looks exactly the same.
Exactly. And the difference between the rotational symmetry of the 2 black and white patterns is that the middle one has order of rotation 2, and the lower one has order of rotation 4. That's
4. Yeah. That's really clearly explained, Toni. I think that's going to really help people get to grips with the meaning of the order of rotation.
Well, it's not important you understand these mathematical terms unless you're going to do a test.
But, yeah, but no, it's one of those things that bothers you when you even after you've left school, you're like, oh, what was that again? And just seeing it again and having it so beautifully illustrated is, I find it quite soothing. Like, oh yeah, I get it.
Now this is so pretty. This next, oh no, it isn't. This isn't what I thought it was
That's
going to
not
be.
pretty. Well, it's not pretty.
Oh, okay. Well, this isn't the slide I thought it was going to be. Where is the slide that I was looking for? Anyway, we'll talk about this one now. We've got it up here. Now here we're looking at reflections. And this is what you might call the Versailles effect. In the most famous hall of mirrors of this type is in the Palace of Versailles. And you see yourself reflected again and again and again in parallel mirrors. Can you explain what you see in the picture there, where there's a girl taking a photograph? And in some of these reflections, she's facing us, or more or less. And in other reflections, she's sort of half turned away from us.
Yeah, like 90 degrees. She's rotated 90 degrees facing away.
I think she's rotated by a half turn, Caroline.
Really? Oh, of course. No, you're right. It must be a half turn, but it looks as though it's 90 degrees. It does look like she's rotated 90 degrees. Oh no, I don't know why. I know why it's the mirror is the full, but because she's at an angle, I think you'll find that she's 90 degrees one way and 270 degrees the other way.
I think she's 90 degrees. No, these are parallel mirrors, and she's not square onto the mirror. That's
the problem. Yeah, that's what
is confusing you.
Yeah, yeah.
She's not square on. She's sort of she's turned away from the mirror slightly, and
yes.
and she's wanting to see in her viewfinder. She's wanting to see this picture that you see, and that she's taken the picture, and there she's it is.
The picture is fantastic, and she's taken that picture herself. It's just so good. I haven't attempted to take a picture like that, and I haven't got anywhere near as good a one as she's got. She's in a lift though, isn't she? She's found herself in a lift. I've just noticed it. I've just realised.
Is she in a lift?
She's in a lift. I've just seen there's a little no smoking sign, and it's got that barrier. I hadn't thought about it. Okay, I'm going to keep an eye out for a lift that gives me this opportunity.
with a mirror on both walls, yes. And of course, if she was facing the mirror square on, she herself would get away she would get in the way of her own picture.
Which is what I have done. So now I know I'm not looking for the square on. I'm looking for that. That's my objective now. Get one like that.
Okay, so now let's get a little bit more mathematical. Well, it's all there, isn't it? Why do reflections in two parallel mirrors combine to give a translation? Now we're going to think about that, and it says on this slide, try it out for yourself and draw the two images after reflection in mirror 1 and then again after reflection in mirror 2. Now this is, on this slide, what you see is what we call a meme, M-E-M-E. It's actually a starter, and every day I put one on the Aiming High website. And you see there in blue the link to the Aiming High website. It's aiminghigh.aimsec.ac.za. ZA, because we're in South Africa. AIMSEC is in South Africa. Well, it's based in South Africa.
The link is in the description, or whichever way, whichever medium you're on.
Right, and you have hundreds and hundreds of what we call learning packs on the Aiming High Teacher Network. It's a website. And each learning pack has got worksheets and lots of other goodies for anybody who wants to play with mathematics or seriously study mathematics. And it's there with resources and ideas for all ages, from preschool right up to the school leaving and beyond.
But I don't see it that way, Toni. Yes, it's there for someone that wants to seriously study mathematics, but I see the learning packs as a really useful activity, that have really useful activities in them for parents that just want to do, like we're going to do over the summer. We're going to do the summer camp. Over the summer, we're going to be using the Aiming High activities with families, playing games. So it isn't about, I mean, I know, yes, they are good for serious learning, but they're you get the serious learning out of having some great enjoyment from the wonderful activities that you've come up with.
So I suggest that if you're here watching us now, you probably, we've been talking for half an hour. If you're still with us, then you go to the every day, if you like, or now and then, you go to the AIMSEC Facebook page. That's facebook.com/AIMSEC-SA.
Again, that's in the description.
You go there, and every day you'll see a meme like this, which is a starter or a taster, if you like, for a delicious meal of mathematics. But this is just the starter. And if you want more of your feast of mathematics, you have to go to the website itself. So that's Mirror Mirror. And what Caroline was talking about earlier on is this mirror, mirror on the wall, who is the fairest of them all, and so on.
Yeah, okay. That's the one.
Now let's have a look at this. Focus on those blue flags, B1 and B2. What's happening? Right, they are reflections of each other in mirror 1. B2 is the image of B1, or the other way around. Now focus on B2 and B3. Just sort of tune out B1. Just look at B2 and B3. Now what you've got is reflections in mirror 2. So B2 goes to B3 by a reflection in mirror 2. So now think of first going from B1 to B2 and then from B2 to B3. 2 reflections in parallel mirrors, and B1 goes to B3. Oh, that's not a reflection. That's just a translation.
It hasn't changed at all apart from its position.
It's just moved along across perpendicular to the mirror lines. So it's twice the distance, if you look at it. Going from B1 to B3 is twice the distance between the mirror lines, and the translation is perpendicular to them. But that's a rather special combination of reflections, because those are parallel mirrors. What happens if the mirrors are not parallel?
Now, we did this, didn't we, Toni, a few weeks ago? Oh, I hadn't seen this slide. Toni sprung this on me as a nice surprise. Isn't that beautiful? And the thing is, you think this is really, really, really hard to recreate.
Well, it's the secret. It's the secret of kaleidoscopes. If you, I haven't got one now. Oh, I do have a kaleidoscope. Actually, I've forgotten. It's a tiny one. Okay, I must have another look at it. A kaleidoscope is a tube with some coloured glass in it, and every time you shake, and mirrors in it, okay, and every time you shake it, you get a different pattern, because the little bits of coloured glass are reflected in the mirrors, and you get these amazing patterns. And you can, the toy kaleidoscopes, you can turn a part of the cylinder around, and the pattern changes as if you change it. Turn it around gradually and gently, you see the pattern changing gradually. If you shake the thing and then look at it again, it'll be, there'll be big changes.
But the thing is, that's because of the contents of it. What I learnt by creating a cardboard box with two basically plastic mirrors was all I had, and then I just made a 2D pattern. I just put something down. What I use is Christmas wrapping paper is all I use. I put that down on the bottom of the box in the corner, and I had two mirrors, just plastic mirrors that I got, like cheap ones, and all I had to do was change the angle between the two mirrors, and the pattern, you had got this effect just from two mirrors, not three, just two.
It
just
is
changing the angle.
It is such fun, and I suggest, you might do this at home with your children as a family. Take two mirrors, perhaps sellotape them at the back, just flat mirrors, and then, as Caroline's idea of the wrapping paper is a good one, but just put anything between the two mirrors, perhaps 2 or 3 little, very small bits of coloured paper or whatever you want, and then have a look at the patterns you get. Now, with this, these 3 patterns, the pink one on the left, okay. Now there you can see, focus on the pattern, maybe these sort of things that look like flowers, like with 2 sort of horns, a little bit like the bull's head, okay. Now you see that if you reflect them once...
Oh yeah, sorry, that's what you mean. They're a bit like tulips, I suppose. They are like tulips.
They are a bit. If you reflect half
You're
of it,
obsessed with bulls, Toni.
If you reflect half of it, right, you get the other half of that same flower, that same tulip.
Yeah.
But then, if you reflect in another mirror line, you get the next tulip round. And that's
it can literally be done by 2 pieces of 2 mirrors, and you just join them closer together with the pattern at the base of them, in order to recreate that.
Yes, and if you count how many of those tulips there are, you'll find there are 9. And if you think 360 degrees, yes. 9 into 360 is 40, so the angle then between your mirrors has to be 40 degrees, and you'll get a pattern with 9-fold symmetry.
So you can predict how many different, like you're going to be able to get 9-fold. You're going to be able to get 360 degrees divided by basically will it be a factor of 360, the amount of symmetries that you can get out of it?
Well, of course, you can have any angle between your mirrors, but then the pattern won't be a sort of perfect pattern. It'll sort of overlap itself.
I'm looking for the perfect patterns. So would the perfect patterns only come out when you actually have a factor of 360?
Exactly. Otherwise, it'll have an untidy edge somewhere where bits overlap other bits. Okay.
I just realised that, Toni. I just had an aha.
So now the middle one, the purpley one, that star shape is 6 points now, not 9, isn't it? Okay.
6,
and
yeah.
But it's formed in a similar way. If you imagine the point of the star, then it's got a line of symmetry, so it's got a mirror line down the middle of it, and then to get it to get the image, which is the next point of the star, there's another mirror line, and because there are 6, those 2 mirrors intersect at an angle of 60 degrees. And this pattern gives you 6-fold symmetry. Okay. And
now I'm looking at the other one. 2, 4, 6, 8, 10, 12, 14. I see 16, and I'm not getting in. I might have got that wrong.
16's right. 16's right.
Okay.
Now, half of 360 is 180. Half of that is 90. Half of 90 is 45, and half of 45 is 22 and a half.
Yes.
So if you divide 360...
Oh, it's the angle. It's not the amount of folds, it's the angle. Thank you. No, I was missing a step. Lovely. Thank you. Go ahead. Sorry.
So your angle is at 1/16 of 360. Okay. And you get the same sort of method of making the pattern with 2 reflections in mirror lines.
This is fantastic. The mathematics of kaleidoscopes. I love it.
In each case, we have to have a center of rotation to describe the rotation exactly. We have to say where its center is, and its center is right in the middle where the mirror lines
where
cut
they
each
meet.
other.
So they must meet. It wouldn't work if you had them. They weren't
exactly
meeting.
And so generally you can see that two reflections give a rotation, and its center is at the intersection of the mirror lines. In general, I mean, we've got lots of these patterns, whereas we've only got one pattern where you've got parallel, because there's only one way two lines can be parallel, two mirror lines, but there's lots of ways that the two mirror lines can intersect at different angles.
Yeah, beautiful.
So there's your pretty one.
That's my pretty one.
Now
here's a different sort.
Here you have. Well, I saw it described as a turtle, but Caroline insisted it was a dinosaur.
I asked Yvette. I didn't say anything. I didn't say anything about it. I asked her what it was, and she said it was a dinosaur too.
And I think the camel is very clearly a camel.
Yeah. Yes. I agree there.
Now, just take some squared paper and draw your own beastie. Okay. It could be anything you fancy, but the big challenge is, can it be such that you can tile it, you can make it up of these smaller tiles, and they've got 4 squares in them, okay, and you can turn your tile round any way you like, but you've got to fill the shape with these, what they're called tetrominos. You know what a domino is? Lots of people have dominoes that they play this game dominoes with, because that means 2 bits joined together, 2 squares joined together. This is 4 squares joined together, and you can use those tetrominos to tile your dinosaur or to tile your camel. What fun.
The thing is, you can't just, I'm just doing a little bit over here, and I'm using a pencil, and I have my rubber available, my eraser, because you can't just place them any old way, and you have to cover every single square, and you can only use that shape. So you might have to do a bit of experimenting, but instead of cutting them all out, I'm just using a pencil and an eraser so that I can, if that doesn't work, I can have another go. But you got to think about it. There are some things that they can only go one way, and they give you a starter clue, a bit like Sudoku. But there's others that can go several ways, and you've got to see if that prevents you from solving the puzzle.
And yes, and as Caroline says, if you use an ordinary pencil and just shade lightly or draw the outline of your tetromino, and then you can rub it out, because it's very likely that you'll put in about 10 of them, and then you'll realize, there's a square here I'm not going to be able to cover. I've got to not necessarily start again, but I've got to backtrack a bit. I've
got this far, and I'm not quite sure if I'm going to be able to use that pattern that I've started with. So anyway, Toni can't see what I'm showing you, so I'm going back to my normal camera.
Well, the thing about this is that there's lots of possibilities here. I mean,
I did it, Toni. I solved it. I did solve it.
Well done. Well done.
It's fun.
And then now, Caroline, is there more than one way you can do it?
And then how many different ways? And have you found them all?
Yes. So there's endless fun here. And of course, you can do it as a family, and somebody may want to use colour, and once they've sort of mapped it out, they can colour it and make it look.
And they can make a poster with all the different ways you can do it. And then you can keep the challenge going. So, can anyone find another way of doing it?
And you can make different animals. So here's some more activities to try.
Yeah, design your own animal and make the puzzle, and then hand it over to your family for them to solve.
But once you've done this with tetrominoes, with 4 squares, how about 5 squares, making what we call a pentomino?
Ooh.
And
Oh, and too, what you haven't mentioned is you don't have to use that shape, that Z shape. You can, as long as you're using 4, so it's a tetromino, as long as you're using 4, you can make different ways.
yes, imagine an L shape made with a tetromino. You'll see one in a minute.
Okay.
So what about pentominoes with 5 squares, or hexominoes with 6 squares?
There's even more different ways you can join those. You can have a lovely zig with a 6. You can have like steps going up.
Now, what about the H shape that we used earlier on? We looked at. We used it for tessellation. Is it one of the ominos?
It's a 2, 3, 6. It's a sevenomino, a septomino.
Yeah. Yes. So yes, there's all sorts. You could be
now that would be a challenge, making a creature that's made up with in squares, made up with H's. That would be interesting.
Well, you can be endlessly creative here, and here are some more examples.
Oh, I like that question. You're not telling us which tetromino can you use to tile the penguin and the robot giant. So you've got to figure out what the tetromino shape is before you can attempt to tessellate it, and you've got to get it right in order to tessellate it. Or maybe there's more than one shape that could tessellate. More than one tetromino that could tessellate the like for the robot, we can start with the H for the head, but then there's no way of doing the neck. Interesting.
Well, there you go. I mean, well, here's a clue. You can do it all with tetrominoes because the H is a septomino, but it's easier with the giant robot or robot giant there. Well, they're a bit out of proportion, aren't they? I mean, the robot truly is a giant. He's taller than an elephant. But then
the penguin. It's a penguin giant as well.
I think I might be quite frightened if I encountered a penguin that was that big.
Maybe the elephant's just a baby elephant that's only like a meter tall or something. Maybe that's what it is.
So it's a little tiny baby elephant.
Yeah.
But we've talked about scale, and we've done paper aeroplanes and things like that, haven't we, Caroline?
Yeah.
And the thing about it is, you look at a picture and you fix on something that you know the size of, and you judge everything else in the picture by one of them. And logically, everything should be to the same scale. But here, our penguin and our elephant clearly are not drawn to the same scale.
Right, and that's okay, as long as they don't need to. But if you want to draw them to the same, you could actually modify your pictures so that you've got more squares for your giant and less squares for your. You can just use a bigger piece of paper and make the giant to scale, to whatever scale you want it to be.
So what we've done today is we have sort of ranged across this whole discussion about tessellation and tiling. And we have provided some fun activities that you could do as a family at home, or you can take very seriously as a grown-up and be creative if you're very artistic and make your own shapes. There's lots to do here. In the applications, we haven't talked much about the applications of this idea, this idea of tessellation.
No, not at all.
Well, I heard a talk by a physicist, a particle physicist, and what he said was that particle physics was all about symmetry groups on different particles were each defined. You could recognize one or another one or a different one by their symmetry groups. So we're talking now about physics, and we're talking about groups.
And when you say particles, is that we're talking about very small scale?
You know, at CERN, they've not very long ago found a new particle that. So we're now going to the smallest bits of matter that there can be, and they put these particles or whatever material in this accelerator, and they whiz it round at very high speed, and they produce these particles. And theory tells them that there's going to be a new particle, but then they haven't actually seen it. So seeing is believing, and they do these experiments to actually produce a new particle.
Yes.
And well, I don't know much about it, although I'm talking on about it. But the groups that we're talking about are mathematical. Now, in some countries, in the last year of school, they do study groups. You do study groups, but actually you meet groups in primary school without using the name.
Okay.
And groups are very simple, actually. Groups are, well, very simply, when you've got lots of things in the group, okay, we call them elements, okay, and you combine two of them in some way or other. Now, it might be numbers and you might be adding them, and you get a new thing. And if we're talking about a group, one of the conditions is that the thing you get must be in the group. So you can't get anything outside the group by combining two things in it. Okay?
Okay.
Now you can combine something with itself, and you can, so yes. So, well, let's talk about the ways of combining.
I should have a clue by now what we're talking about, and it's not happening.
Well, all right. So, okay. So let's think about addition of whole numbers.
Are you talking about factors?
No, I'm talking about addition of
no,
whole
I mean
numbers.
the groups.
No, the group is as follows. You when you add two whole numbers, you get a whole number. So
yes.
the answer's in the group. Good. That's one of the things.
Okay, so a whole number would be a group? It's a whole number?
No. Just be careful. All right. The whole number is one of the things, elements of the group. Okay.
Okay.
Now then, if you do something with a member of the group and you get another member, then you can reverse that operation, right? So you can get from +5 to -5, and you can go back again.
Okay.
And when you combine them, if you add +5 and -5, you get no change. So in the group, you have to have two things that you can combine, or you can follow one operation by another, by the same operation, and you get back to where you started. They're called inverses.
Oh, okay.
Yes, okay. You know about inverses. Stand up, Caroline.
Stand up. Inverses.
Stand up, sit down.
Sorry, stand. Oh, yeah, that's stand up. Yes, that's standing up, and that's sitting down, and that's the inverse of that, or
that's the inverse operations.
Of that. Woohoo! I'm falling.
So every operation is you've got to have inverses, and you've got to have and the inverses combine to give you the identity, which is staying the same.
Yeah.
And so what I'm saying is that everybody meets groups in primary school, but they don't call them groups. All this arithmetic in primary school is actually working with groups, but you don't use all this fancy mathematical language, and probably until you get to university.
Okay, yes, I've heard of group theory as something people study in university, and you mentioned group theory to me, and Alan does. But
some people, Caroline, spend all their life studying group theory.
Yeah.
And then, as I said, this particle physicist, when I heard his talk, He was saying that particle physics is all about groups, and the way you identify different particles is because they've got different groups. Isn't that funny?
That is that, and then it's identifying new discoveries, and by using mathematics.
Yeah, and so when we started talking, we were talking about the bull tessellation and the H tessellation, and how, in some sense, there was a similarity between them, because we could see a parallelogram in each one that moved to other parallelograms to make the tessellation. But then we looked a little bit more deeply, and we saw that the H had got reflections and rotations in it. And the bull didn't have any symmetries like that. So they were actually different symmetry groups.
Yeah.
And so when we talk about 17 wallpaper patterns, we're talking about 17 symmetry groups. And what we're saying is we believe that the Moors in Spain in the 14th century knew that there were 17 because they very clearly represented them all on the walls, with the decoration on the walls.
Right.
So
and they represented all 17 of them. They're all there.
And to a lot of people, I'm not sure it's really true of Christians, but a lot of people, a lot of religions, they regard mathematics as, almost in awe, almost as a spiritual thing.
Well, in Islam, they don't have any representations of people in their art, in anywhere where in the religion part of things, there's no pictures of people. It's only geometry, abstract.
That's right. But I mean, if you go into Israel, and I believe that in their teaching, it's almost a religious duty to go to study and learn more about the world around you. And if you think, if you go to temples in Japan, you find there that they have tablets or pictures in stone of mathematical problems, and the idea is you go and you sit and reflect about that problem, and you sort of enter the world of mathematics and get absorbed in thinking about the problem in the temple.
Going into a trance, meditating on mathematics. Yeah, easily done. You completely you go somewhere different. Well, you go you get so deeply engrossed in it that you're not really aware of other things. You're clearing your mind of everything else. You're not really, there's no room to mull over your life's problems when you're focusing on solving a mathematical problem.
So to go back to our wallpaper patterns, we've been doing this in 2 dimensions, but then go to 3 dimensions.
Which presumably is particles will be in 3 dimensions.
Absolutely. But also another application in science is with crystallography. So I believe, I'm not sure whether it was his brother, Escher's brother was a crystallographer. And I think that is what, made him aware of and thinking about shapes fitting together.
Can you imagine the conversations?
So crystallography is another area of science which uses this mathematics of the idea of groups of transformations.
And all we're doing is tessellating a plane, tessellating a little robot. Well, a big robot. We're not sure if it's a big or a little robot. That's all we're doing. And yet we're having the first experiences of some very complex mathematics.
And finally, the difference between tessellation and tiling is just filling up the area with the same tile, the same shape, but not leaving any spaces anywhere. Okay. But tessellation is doing it in a systematic, regular way which has a repeated, which has a group structure,
which has one of the 17 group structures of your wallpaper.
Yes.
Okay. So tessellation. So if you just had white tiles, that isn't tessellation. Is that correct?
It is, yes, because
it is tessellation.
Yes, because you've got the simplest of the simple.
It's the simplest. It's the simplest. It's got everything. It's symmetry everywhere.
Yeah, absolutely.
Every which way you go, it's symmetrical.
Especially if they're square. Yes.
Especially if they're square, right?
But now, if you take these tilings of the elephant and the other creatures, then I think you'll have to turn your tetromino round different ways, and it won't be repeating a regular clear pattern.
Yeah, I mean, doing the camel, I've had to rotate in a number of different ways and reflect them, and there's definitely no pattern there. So
right.
So I can tile. I've tiled my camel, but he's not tessellated because there's no pattern.
And there's a well-known mathematician at Oxford. Oh, he's an old man, retired now, like me. I'm not an old man, but I'm
not an old man.
I'm an old woman, long retired. Okay.
Vibrant.
Yeah.
Woman, vibrant and mature woman.
Oh yeah, definitely. Well, I don't know about that, but anyway, let's not go there. He's called Roger Penrose. And he did a lot of wonderful mathematics, still doing maths for all I know, but he made special studies of tessellation and tiling, and he and Escher were quite friendly, and they helped. It's said of Coxeter in yes, I did meet Coxeter and talk to him about it as well, who is an English mathematician who spent most of his life in Toronto. And these two mathematicians and others were influenced by Escher, because Escher had such wonderful vision, but Escher also learned a lot of mathematics from them. So I think there's time to leave it.
It is, and I recommend that you look up Penrose tiling. I've just googled Penrose tiling Oxford. I know outside, I don't know what they call it, the maths centre, the maths building in Oxford, they have Penrose tiling in his honour on the way in there. So thank you so much, Toni, and we'll see you next week for another happy maths hour. We don't know what it's going to be yet. It'll be exciting, whatever it is. Thank you for your presence and for Toni's hard work. Toni does all the hard work here. I'm like just the support crew.
Okay, well, we'll see you next week.
Thank you. Bye-bye.